Well, today we'll talk about mobility of solutes in the vadose zone. And so far, to put this all in perspective, in looking at the behavior for our system, what we've done, is we've looked at the behavior in the subsurface to where the fluids go over the first few days to weeks, how they're held in place by interfacial forces and don't move. If they do move, it's controlled by relative permeabilities. So that was the first topic we dealt with, and we can calculate the rates at which fluids will move as fluids themselves. Then we spent the last little time from section 3 onwards talking about the rates at which components will dissolve out of this and travel down gradient driven by groundwater flow and dissolved in water. And we've divided that into two formats: conservative flow, where everything remains in solution, nothing comes out and sorbs onto the solids, and non-conservative flow, where sorption occurs, and as a result of that there is some kind of retardation. And we know that as a function of that, if we kind of draw in schematic form what plumes look like, we know that they are defined by both conservative flow, where we can get magnitudes of how far things go downstream as a function of, I suppose, the length traveled. Velocity is equal to length over time, so velocity times time gives the rough length traveled. If we divide through by what we've referred to as a retardation factor, then we get these two very different behaviors when we have conservative. So this would be conservative when R is equal to 1 only, and non-conservative when R is by definition greater than 1, so sorption occurs. And we know that we can define these behaviors in terms of this retardation coefficient, which straightforwardly we defined as the conservative case only, which is 1, plus bulk density of the aquifer, either porosity or volumetric moisture content, and this term called the distribution coefficient, K sub B. And that was useful to us in being able to define behaviors, because we could use that, for instance, to define this lag in the I guess multiple things. Define this lag in the progress of the front through the system, the fact that the front would self-sharpen. So the larger the value of the retardation coefficient, the sharper this front would be. And it also conditions the behavior in terms of arrival. And so I can't, perhaps I'll do it separately here. It's blowing a gale outside. If we look at arrivals in terms of the residence time distribution curve, RTD, for relative concentration, I guess this would be 1, right? And this would be 1 as well, C over C0. Then again, we expect to get this behavior where the arrival time, if we just rearrange this, so time is equal to length times retardation over advective velocity. And when retardation increases from 1, then if I go back to the green curve for the non-conservative case, it just delays this arrival. And I suppose this should be steeper than this, although it's not drawn that way because of this idea of the sharper, the front sharpening as a result of retardation. So that's kind of the story so far. It has all been within the saturated groundwater zone. And so now what we might want to look at is the behavior of what goes on in the zone above this. And of course, for any stuff that gets filled on the surface, it has to make its way through the vadose zone to get to the tension saturated zone and the groundwater zone. And so some of it potentially will get hung up in here, in this chimney that we've talked about, which is present at maybe relatively low saturation, and in this lens that might capture it based on low permeability or high capillary entry pressure behavior to cup a lens here that will hold it in higher saturations. And you can imagine that in this zone, which is mainly saturated by air and not by water, it'll have some water for sure, but mainly air saturated, what are the mechanisms by which the dissolved components dissolve now in air instead of in water? What's the mechanisms by which those will travel away from this? And so that's our task today, is to basically understand volatilization of these things here and the mechanisms by which they'll travel. And so there's a big parallel to what we've talked about so far, and that is that you can imagine that in these being transported, they will be subject to the same advection dispersion equation that we had for groundwater flow, but the medium will not be carried dissolved in water, but it'll be carried dissolved in gas, and so vaporized in gas, if you like. And you could imagine also that if we have sorption of these components onto either grains in the aquifer or organic carbon in the aquifer, you could think that the same behavior might occur to take the stuff out of vapor phase and put it onto the aquifer in the vadose zone could occur as well. And if that were the case, if sorption occurs there, and there's no reason why it shouldn't, then we'd expect that we'd have a retardation effect, which would be somewhat similar to this in the vadose zone. So that's kind of our task for today, to be able to understand those mechanisms. So we're going to talk about vapor mobility, and as we've alluded to, we could imagine that we have very similar mechanisms acting in the vadose zone as before. We get transport, which we're interested in because that's the only way that it moves from a location to where it can do some harm. It can be damaging in going to some compliance location, or it may be the mechanism you're interested in reducing the amount of mass in place by doing something like soil vapor extraction. And the mechanisms we can use to move it are both by diffusion and by advection. We will only look at one form of advection. And the same behaviors that we looked at for non-conservative transport in terms of the partitioning of the vapor phase into the solid can happen. And if that does happen, then the plume transport will be retarded. And so we'd like to be able to figure out exactly what is the value, for instance, of the retardation coefficient for gas transport. So that's our plan for today. So this is kind of a cartoon of what you could imagine is going on. So you have a spill. It has to go through the vadose zone to get to the groundwater zone. It'll get held up by capillary forces. It'll be present at a variety of different saturations in the vadose zone. Some of them may be quite low, maybe 10-20% saturation of NAPL. But it can do a variety of things. You could imagine that it could diffuse in air, just as the analogy would be if I was smoking here, which we don't do, of course, anymore. You'd be able to smell it where you sit, and that's a diffusive process by which Brownian motion takes the odor, the particles of smoke, from one location to another. So here you have vaporization of this. It becomes a component within the air-filled pores of the vadose zone and can travel driven by concentration gradients, just as it could in water, driven by concentration gradient in water. Typically, if it vaporizes, it's denser than the air, and so there'll be some advective components that would drive flow downwards and into contact with the water table. Once it's in contact with the water table, there's no reason why it can't dissolve into the aqueous form. And if it dissolves, there's no reason why it can't be carried downstream in pre-existing groundwater flow, driven by a slope in the water gradient. And this diffusion and advective flows can be also affected by the amount that is taken out and attached to the aquifer, the vadose zone aquifer, and then lost to transport. Plus they can vaporize into the atmosphere and be blown away by the wind. And perhaps most importantly, as we'll see, the impacts of infiltration is that in going through this, it can pick up a loading not unlike the loadings you'd expect to get by dissolution in the groundwater zone, and it can carry this as infiltration plus dissolved components into the groundwater zone and then have it transported away from that. And so we'll specifically look at we'll specifically look at two mechanisms by which that can occur. And we'll look at the first two of these because they're, I guess, they're increasing complexity as you go from left to right. The easiest one for us to deal with is just straight diffusion. It finds its way into the subsurface, it sticks here by interfacial forces. Perhaps it doesn't look quite like this blob, perhaps it looks more like this chimney that we've been used to seeing with lenses attached to the chimney somehow, but where this zone is of relatively low saturation with a architecture that has lenses of high saturation. But from this location, it can just diffuse in the pore space, the gas pore space within the aquifer. If we add an extra layer to this, then the other form would be rainfall, picking up dissolved components from this and adding those to the water table, from which it can be carried away with the normal flow of the groundwater. And one which we won't deal with because it's perhaps a minor effect and it's complex to deal with, it's not one of the two major components, is by density-driven negative buoyancy, I guess, right? Density-driven flows, which again drive gas flow within the subsurface. So what we'll do, we'll talk about these first two. We'll deal with the first one first and the second one afterwards, but we'll try and talk about the different mechanisms by which this transport can occur. And so diffusive transport is no different from the behavior in the saturated groundwater zone, except now the driving flow is the concentration gradient of the gas. TCE dissolved in a mixture of nitrogen and oxygen, which is air, and that concentration gradient in space. It directly follows Fick's first law, which defines that this is, I guess this is a mass flow rate per unit area in the way that's written. So this is a concentration gradient. This is a gaseous diffusion coefficient. I guess it's written down below. Always be in meters squared per second is units. And the star refers to the fact that it's modified. It's modified because instead of the straight diffusion coefficient, which would get you the smell of smoke from a smoker sitting in a room, you could imagine the room being filled up with sand, an aquifer, and it has to wind its way through the pore space. So it's modified by the tortuosity of flow. And the second thing, that in addition to this modified tortuosity, the cross-sectional area that it has is really one that's driven by the cross-sectional area to gas flow. So theta G is just the volumetric gas content. So if your porosity was 20% and there was no water in the system, then this gas content would be 20%. If it's 20% porosity and 50% saturated with water, 50% saturated with air, then this would be half of the 20%, which would be 10%. So this is the gaseous, volumetric gaseous content, volumetric gas content. And so in the same way that we dealt with advection diffusion equation for transport dissolved in water, we substitute this flux Fick's first law into a conservation equation, which says mass in equals mass minus mass out equals accumulation. And if you do that, you end up with this diffusion equation, identical to the one that we had before. And so identical to the one we had before is that it has a retardation coefficient, which we haven't said what it is yet. We'll have to define that, which we could imagine does something as a function of sorbing components onto the static solid phase. And we can do just as we did before. You could imagine dividing both sides through by retardation. This becomes 1. And you have a diffusion equation, which is in the form that we're used to seeing it, that is a concentration gradient in the gas with time, concentration with time, and an effective diffusion coefficient, effective in a variety of different ways, and driven by concentration of components in the gas phase. So this is just rewriting this in that way. And so this doesn't include convection. We could, if we wanted to, I suppose, add a term which is advective gas flow divided by retardation and dc dx, as we had before. This would be the advective term. And so I should make sure I'm attaching that only to this left-hand equation. And that would be fine, but we're just going to ignore that term in the things that we'll talk about, just because it's a little more straightforward for us at present. We could do all the same kinds of back-of-the-envelope calculations we tried with pushing fluids and dissolving stuff in the saturated zone. You could apply them equally well here. But if we look at diffusion only, then you could imagine that, for instance, this source that you have in the system is able to diffuse away, and the meaning of retardation coefficient is exactly the same as before, and that is that the form of this concentration distribution away from the source, it will look like this at one particular time. I guess if we looked at a later time, it would look like this. So this might be T1 and this might be T2, and so you could imagine the Gaussian distribution, the normal probability distribution curve spreading as a function of time, and we've talked about that in 3.1, I guess, when we were talking about this. And so this you'd expect to spread with time, but our main interest here is the meaning of the retardation coefficient, even though we haven't yet defined it. And it means that it just shortens the length that's traveled in direct proportion to the magnitude of this retardation. So if it's gone 10 meters in 10 days, and it's a conservative species, if there's a retardation coefficient of 2, then it would go 5 meters in the same amount of time. And so it just gives that same scaling. And so we need to be able to define these parameters that describe this system. So one clearly is the effective diffusion coefficient, and one is the effective retardation behavior. And so we need to define at least each of those components. So the effective diffusion coefficient is the straight diffusion coefficient for the gas, and so this might be typically of the order of 10 to the minus 6 meters squared per second. Typical diffusion rates of odors in air. Compared to maybe in water, diffusion coefficient in water is something maybe 3 orders of magnitude slower. So TCE in water might move 3 orders of magnitude lower diffusion rate than in gas, as it turns out. But also pre-multiplied by a factor which represents the tortuosity. It represents the fact that the flow in going from upstream to downstream doesn't go in a straight line, but has to go on a tortuous pathway that takes account of the kind of architecture of the aquifer. And so you can define tortuosity or that effect in a couple of ways. One way is if you could look at the soil itself, you could define a length between 2 points relative to the length traveled, the straight line length versus the line traveled. And you can define that, the square of that gives you some idea of the tortuosity. But more usually used is this empirical correlation from Millington and Quirk from a long time ago now that defines behavior in terms of the volumetric gas contents and the total content. So theta T here just means porosity, right? In other words, if it was completely dry with no water in it, then that would be the volumetric gas content. But this is the total porosity of the system. And so the gas content to the power 7/3 divided by the gas content, the total content, or the porosity. So I guess you could write this as porosity. Be the same way of writing this. And so that allows you to be able to say how this value changes as you go down through the Vadose zone. And so since we think that in a gas, diffusion is fast, but in liquid, diffusion is quite slow, you'd expect that as you go down through the soil column, and if you look at this would be the same as a capillary pressure versus saturation curve, or it could be elevation versus saturation, right, as we've drawn it. This is elevation here above the water table. Then as you're close to the water table, you're in the tension saturated zone, and there's the residual air content, maybe of 5 or 10%. And as you go higher up, then there's less water and more air. And so if you do the calculations to look at 35% porosity, which is this, gas diffusion coefficients given by this, 10 to the minus 6 order of magnitude, and do the calculation. Then if you've 25% gas content, you put this into Millington and Quirk, into this. So this is 25% to the 7/3. This is 35% squared. You get a value of this tortuosity, which is 32%. If you multiply that through by the straight diffusion coefficient for gas, free gas coefficient, then you end up with a relatively high gaseous diffusion coefficient. If you go down to the case where you have only 5% and you do the same calculation, then this number then is a much smaller number, and it reduces this by 2 orders of magnitude, 10 to the minus 8. And ultimately, when you're in water, it would actually take on the diffusion characteristic. It wouldn't be 0, of course. If you use this tortuosity, you could imagine that this would actually go to 0, right? If there's 0 residual gas content in the system. So it makes sense that instead you use the diffusion coefficient in water, what we called D star before. So that allows us to be able to define one of the coefficients that we need. And that is we can get the magnitude of this effective gaseous diffusion coefficient. So the other part we need is to figure out exactly what the partitioning is. And so the partitioning is defined in terms of absorption in the system. You'll remember before when we talked about aqueous behavior, we did this thought experiment where we take some grains of the aquifer and we put in water at some aqueous concentration, and we looked at the concentration on the solids as a result of this, and we could draw this curve for the solid concentration versus the aqueous concentration as an equilibrium value, and we got this distribution coefficient, Kd to 1 by definition. So in other words, Kd, distribution coefficient, was just the ratio of the solid concentration, equilibrium solid concentration, to the aqueous one, Cw for water. And so this defined how much of it went onto the solid. So in the system we have solid, liquid, water on the grains, and also gas. What we can do is you can use Henry's law coefficient to define this partitioning at equilibrium in the same way to the amount that gets sorbed into the water within the system as a function of the amount that's present in the gas. So if you know of the absolute solubility in the water, you could calculate what the gaseous concentration would be from that, so long as you know this value of the Henry's Law coefficient. These are both the same variables, both concentrations. So if you define them in the same way as mass per unit volume, this is a non-dimensional term. But usually, which will be useful for us to do, and we'll do that, we'll use this expression. But Henry's Law coefficient, if you look up any environmental or mechanical engineering textbook, is usually defined in a complex form of atmospheres meters cubed per mole. And it's defined slightly differently. It's the same idea. It's the ratio of a gas concentration to a water concentration at equilibrium, just as we have here, except that the gas concentration is defined in terms of the vapor pressure, when it vaporizes and becomes not a separate phase, but becomes a gaseous phase. And so really what's going on here, if you remember, if you imagine that a pressure or a vapor pressure from the ideal gas law is a density RT, or is a density times, let's leave it at that. Then if we know that this is a density, then dividing this by RT and RT gives us a density. And so in other words, since this is really a density per unit volume, there's no reason that we can't represent it as a pressure, equivalent pressure, because pressure and density are related. Increase the pressure, you increase the density. And so that's why Henry's Law coefficient is traditionally written in this term in a dimensional form, but we in our stuff will try and redefine it a little bit later on in this non-dimensional form, because it's convenient to think of it as directly related to the distribution coefficient. It represents a relationship between, if you wanted to, you could define this as a concentration on the solid versus a concentration in the water. And this is a concentration in the gas versus a concentration in the water. So they're equivalent to each other in some way. And so if we're thinking about the partitioning that we could get, clearly you could imagine some of the gas being in equilibrium with the water that surrounds the grains. But you could also imagine that in our saturated aquifer, the water was in equilibrium with the solid through the distribution coefficient. And so we represented that through KD. And if we know what KD is, and we know how much organic carbon we have in our aquifer, actually, if we know what KD is, we can define retardation, right? So KD allows us to get retardation in the aqueous form, which is just as we wrote before, which is 1 plus bulk density, moisture content, and KD. And so I suppose what we'd like to know is what is our gaseous retardation coefficient, because that's what we need. And so this is it defined here. And so you'll see some similarities. I suppose it's best to just talk about what the basic idea is. The idea is that you could have a porous medium which has air, which is the white clear stuff here, the grains, which are these cross-hatched areas, and the water, which is blue. And so we know that when you saturate it, initially if it's only filled with air, then there's no blue, then that's fine. You have just grains, you have just the cross-hatched areas and the white. If you add water, you know that you're going to surround the grains by this monolayer of water, which is here. And also some of the pore space will get filled in with the system. And so you could imagine that one way to think about this is that if you have gas here within the pore space, then the gas can contact the water, because we said that typically the water covers the grains in a water-wet solid at a very monomolecular thickness. So if it wants to get from the gas into the quartz, it has to go through the water. So the hierarchy that's presumed is that the gas can only go into the water, and once it's in the water, it can then be partitioned into the solid. And so that's kind of the rationale of this. And if you do that, then you can get an expression like this. This represents the partitioning of the gas into water. And this represents the partitioning of the aqueous concentration into what we've called solid or C star. And so, not surprisingly, if you use that, then if you look at this, don't cross this out because I'm going to erase this in a moment. But if you physically remove this term here, then you have this expression plus this. If you get rid of this term, this is something that you already recognize, right? This would be the aqueous retardation coefficient. And so all that we've really added in this particular case is this second term that mediates, if you like, how gas goes from the vapor form into water, and then from water into the solid, into the solid. And so in this particular case, we'll use this non-dimensional relationship H, which is the concentration in gas to water, by definition. And so we had to figure out exactly what this is as a function of the normal Henry's law coefficient, which we've called H prime. But we'll defer that for a moment. Okay, so you can use this retardation coefficient that we have. So this is what we'll call our gaseous retardation coefficient. And we can figure out what the magnitude of that would be if we know Henry's law coefficient, if we know the volumetric moisture content and gas contents, and the characteristics of our aquifer in terms of gas contents and KD. And so if you just take a material TCE, which we use because we use it later on today, if we assume that we know the non-dimensional Henry's law coefficient, which just says, I suppose if you rewrite this as concentration of gas multiplied by concentration of water, it says that the concentration in the gas is 0.3 times the concentration in water. That's physically what that means. If we take an organic carbon partition coefficient of 120 milligrams per gram, a porosity of 35%, right? By definition, 10% gas saturation, gas content, 25% gas content, 10% water content. Add those together, that's the total pore space and an assumed density. Then we can calculate each of these two terms. So this one is gas to water, and this is water to solid, these two terms. And if you do two things, you assume an organic carbon fraction. We said already you shouldn't use this expression that we're going to use here if the fraction is less than 0.1%. So this is 10 times lower than that, but let's use it anyway. Calculate the gaseous retardation. It's the same in both cases because it only comes from the gas into the liquid. It isn't affected by the presence of carbon. And the liquid to solid partitioning, because there's a large amount of organic carbon here, by a factor of 100 larger, then the retardation as well, because it scales with distribution coefficient, which will be 100 times larger, is also 100 times larger. And so if you add these two together, you get a very big number for the combined effect with lots of solid sorption in the system, which is affected by the large amount of organic carbon in this particular case. But in the case where you look at very low coefficients of organic carbon, you see that the sorption or the attachment from the gas into the liquid, this would be 0.33, right? 1 plus 0.33. Oh no, actually this is 1.33, is of the same order as the amount that goes from the liquid into the solid. And so you see that there's a major effect, not so much of the liquid, but actually of the solid has a big influence on that. Okay. So the other consequence of this retardation coefficient is that there are the effects for the gas behavior, which we've defined here. And we also know that there are effects for the aqueous retardation. So these are those two expressions just redefined here. So the amount that would be present in the vadose zone, and the amount that would be present within the groundwater zone. And so the effects of each of these would be that they define how far things would travel in a given time. And so when we looked at this, by definition what retardation meant was this idea that if it's gone 10 meters in 10 days and it's conservative, then if it has a retardation factor of 2, in 10 days it would only go 5 meters by diffusion. So we can use that length scaling to define the behavior. But also we could use that length scaling to look at the arrival times that occur at some particular location. And so the retardation factor will also determine the first arrivals in a system. And so what we could imagine looking at, and I'll try and fit it, is that if you have a system where you have something in the vadose zone, which is free product that can volatilize, that can also be present within the groundwater zone and dissolve, then these would both be transported in each of these media by diffusion. And so I guess we'd imagine that it would look a bit like this response that we talked about before. This is the source, and in the groundwater zone, the diffusion profile would look like this. Sorry, in the vadose zone, and maybe in the groundwater zone, if I just do it upside down, it might look like this. So I guess this is CW over C0, and this is C gaseous over C0. And so if you look at any particular single location that you have, one of these plumes would arrive first, right? If you're sampling at this physical location here, this is X, then one would arrive first. Presumably the one that's traveling fastest by diffusion would arrive first. And so we can't very easily define the rates at which they travel, but you could imagine calculating the order in which different components would arrive. So if for 3 different components, given at the bottom here, TCA, TCE, and methylene chloride, we go through and we use the appropriate Henry's Law coefficient, and we use, I can't even see these, the slide is so bad, apologize for that. This is the distribution coefficient, K sub D. I guess I've written them up here, that's why. This is KD, this is H, what I've called H prime. We could calculate the magnitudes of each of these retardation coefficients. RG for the groundwater, for the gas, and the aqueous one for the saturated zone. And if you calculate each of these, you end up with the aqueous retardation coefficients and the gaseous retardation coefficients. And where you have a small retardation coefficient, it should move fastest. So if you look at the size of these aqueous retardation coefficients, you'd expect the first arrival to be one of methylene chloride. You'd expect the second arrival to be TCE, and the third arrival to be TCA. And so that's in the groundwater zone. If you look in the gas zone, then the smallest one now is still methylene chloride, but the second arrival now is switched. So instead of arriving in the same sequence, if you sampled in the vadose zone right directly above the groundwater zone, the order of arrivals would be different, and because they have different influences of these components that contribute to the different retardation coefficients. And so that's maybe a curiosity, but the fact that it would explain why things would arrive at different times. So if we expect that large magnitudes of retardation in the gas means it's delayed, you'd expect it to also travel less far. And so these are just results from an experiment done in a OGI's Oregon Graduate Institute. And it was a fabricated aquifer, which is a vadose zone, so unsaturated. Quite big. It's a big box, so it's 10 meters by 3 meters. So 3 meters is 10 feet, so about as tall as this room. It's probably about the size of this room, that's filled with sand, that has a bunch of capillary tubes placed in it so you can sample. And then at time 0, a mixture of methane, butane, and trichloroethane is injected in nitrogen as a carrier gas, and then sampled at 24 hours on the left-hand side and 3 days on the right-hand side. 1 day and 3 days. And so these just represent contours of how far the different components have gone. And you see that both after a day and after 3 days, the distance traveled is pretty much the same for the first two, methane and butane, by diffusion, not by advection, and much less than that for TCE. And so it should correspond then, if we look at the magnitudes for these gaseous retardation coefficients, that TC, the slowest moving one, should have the largest retardation coefficient. And so if you go through these and you take the values for these Henry's law coefficients, what we've called H, by definition, they have similar magnitudes for the first two and a much lower magnitude for the third. And since the gaseous retardation coefficient is an inverse function of Henry's law coefficient, when this is small, this will give a large retardation. And so it's not surprising then that the ratio of these are roughly the same for the rates of transport of methane and butane, but much slower for TCE. And it comes directly from this understanding of the form of the retardation coefficient. So if we can get this magnitude, then we have everything we need to be able to do the things that we've talked about doing to make these kinds of predictions. The problem being that usually when Henry's law coefficients are quoted, they're usually quoted in terms of a function of vapor pressure and solubility in water. And so the value of H prime that we need is modified. So what we can do is we can think about transferring H prime to get to the one that we actually want. So if you get this from a table in a textbook, how do we convert it? So we can just manipulate it. So we realize that vapor pressure is really a function of the ideal gas law. The ideal gas law defines the pressure in terms of a density, a universal gas constant, which is defined here, and the molar mass of the particular solute in this particular case, and the absolute temperature. And so we could substitute that in here. We realize that concentration, it can be defined in mass per unit volume, but it can also be defined in moles per unit volume. And so maybe it's convenient for us to use moles per unit volume in here. So if we make that substitution for each of these two expressions, here and here, into this, we end up with this expression here. And if we then remove some of the components from this, so in other words, if we just define this in terms of those components to separate them out, then it allows us to define this dimensional Henry's law coefficient, conventional Henry's law coefficient, as a function of this ratio and gas constant and temperature. And so the important thing about this is that this is a concentration, if you like, of the gas and a concentration of the water. And so by definition, this term here, if we choose appropriate units for it, I guess I could just draw on this. This is concentration, by definition, Cg over Cw. And so if we rearrange this, then we end up with concentration in gas over concentration in water is equal to this term divided by RT. And this, by definition, is our definition of H. So this is what we want. And so now if we know what this is and we divide through RT, then we ultimately have it. So it's nothing more than that. And so if we do that for TCE, if you go and look up the Henry's Law coefficient in a reference text, you end up with 9.1 times 10 to the minus 3 atmospheres meters cubed per mole. You substitute this in to here for the appropriate universal gas coefficient, which is up here. Then you should end up with a value of Henry's Law coefficient, which is about 0.4, which just represents clinically the ratio between these two equilibrium concentrations of gas and water. So in other words, if you have something dissolved in water, that's the solubility for TCE, which is maybe 1,000 milligrams per liter, you can immediately, if you know this coefficient, calculate the equilibrium concentration in the gas above that. Or if you do the converse and put it in gas and measure the concentration, equilibrium concentration water, then they have to be in the same ratio because it's an equilibrium behavior. You can check it with values from literature. It's a function of temperature, and so you can make those checks. But here is a value for the vapor concentration in kilograms per meter cubed for TCE. If you know the saturated concentration in water, the solubility is something like 1,000. So if you take 520 milligrams per liter divided by 1,100 milligrams per liter, you end up with something like 0.5. This happens to be at, I think, 25 degrees, if you see that, compared to this one was at 20 degrees centigrade. So they're slightly different, but you see they're basically the same number, just a non-dimensional ratio. The other thing I suppose we should mention just quickly is that we can also use Rowels Law. So this is okay. So this is also Rowels Law. And it's no different than before. It says that it's easier to write it out as concentration of gas for component I is equal to the mole fraction of that component multiplied through by the free phase component. So I know if you know what the equilibrium concentration of gas is when it's 100% methane in air, and if you know what the mole fraction of that component is, then you can calculate exactly what the magnitude would be if it's competing with other gases to get into vapor form. And so knowing the mole fraction of the components in the liquid form allows you to be able to get from the values of the gaseous concentrations, calculate the effective gaseous concentrations. So this would be the effective gaseous concentration. So this is what we call it free phase gas concentration. So it's just the same idea. If you have more than one component, they're competing to be sorbed into the air, if you like, I suppose. So those give us probably enough to be able to deal with behaviors to talk about the first of our systems. And so the second of our cartoons that we're dealing with was the effect where we don't just have diffusion, but we have advective flux. And the most important advective flux for us is due to infiltration. The idea being that you can pick up dissolved components as water infiltrates through the vadose zone. It picks up a loading and then it dumps this loading onto the water table as it reaches it. Has two effects. It will remove it from this part that's held here by solubilizing it and removing it to the groundwater table, which is probably good. What's bad is that it arrives at the groundwater table and then it's free to be transported with the groundwater flow to some compliance point where you don't want it. And so our way of looking at this is to look at it relatively straightforwardly. And that is to use what we've talked about before. And that is that we know that in the saturated zone, we can get an advective velocity, which is equal to the Darcy velocity divided by porosity. So this is, we've called it aqueous, I guess, right? It's confusing. So this is aqueous. And so the idea is that the Darcy velocity gives you the bulk flow. It's only flowing through the cross section, which is the porosity. And so porosity is always less than 1, so it speeds up the actual flow relative to the Darcy velocity. So you can imagine the same happening in the subsurface, where the advective velocity is equal to the Darcy velocity, which is infiltration. So this is the infiltration flux, which is a velocity. And so if you get 0.45 meters of rain a year that has to go into the groundwater, then this is like a Darcy flux, right? It's 0.45 meters of water per year spread out over a square meter. And so if you multiply this by a square meter, it would give you a volumetric flux, which would be 0.45 cubic meters of water per year per square meter. And so if you think about the fluid which is moving through the vadose zone, it will flow only through the part which is saturated with water, because we're expecting that the saturation profile as you go up through the vadose zone doesn't change very much. And so it's only the part that is filled with water that will conduct this infiltrating fluid. And the part which is filled with water is going to be the volumetric moisture content of the system. So instead of being the porosity that it's going through, it's restricted only to flow through the originally water-filled part of the pore space, which is given by the volumetric moisture content. And so if you know this in the profile, and if you know the rainfall at a site, and you assume that everything that hits the site gets infiltrated, you can calculate the advective velocity for it to hit the water table. And so, for instance, if the advective velocity, I think, is equal to 2 meters a year, and you have to travel 1 meter, then you know that it would take about 6 months to get there, right? Just from looking at this. So that's one way that you can use this. I guess if you knew that you're starting only half a meter up from the groundwater table, then I suppose the relevant time scale for you to look at was for it to travel this half meter. So once water infiltrates and starts from here, then I suppose actually it would only take 3 months to get there, right? Because it's only traveling. It's starting here, it's traveling half a meter. If it takes a velocity of 2 meters, then it'll go that length in a quarter of a year, not half a year. And so the one thing we can calculate then is the time taken to travel. I suppose this assumes that R is equal to 1. If R is greater than 1, then I suppose the value for this advective velocity would be equal to infiltration rate divided by volumetric moisture content and divided through by retardation. Both of these on the bottom. Right? So it would be traveling slower because it would be, if R is 1, you get the same result, and if R is not 1, you get a different result. So I guess you could just multiply this by R to get the retarded magnitude. And so that's one question that you might want to know. How quickly does it get down there? Is it fast or slow? Is it never going to get there, or is it going to happen very quickly? And the other thing you might want to know is what is the mass loading once it hits there. And so there's a delay before it gets there, but we'd like to be able to calculate the mass loading. And so the mass loading is similar to before. This will be the Darcy flux, QD, multiplied by its concentration. This would be solubility. And so in terms of the parts below, this is the Darcy flux, and this is the effective solubility. The Darcy flux is just the advective flux multiplied by the cross-sectional area of flow by definition. So this is the same advective flux that we had before, and this is the volumetric moisture content. And so if we know the values of this, from here, then we can calculate exactly what the mass loading. So those are the two things that we might want to be interested to determine. And so just to cement those concepts, this was an experiment that's also done at Borden, the same place that we have those chloride and carbon tetrachloride plumes that we worked on last time and the time before. A slightly different experiment to put in place, dig a hole and backfill a little cube that's 30 by 30 by 45 centimeters in dimension, half a meter below the ground surface, that has a liter of TCE that's spread within the sand that is backfilled, basically at residual saturation. And so the two things you might want to calculate, one is how long does it take to get to the water table, and what is the mass loading if it does get to the water table. And so these are just the calculations to be able to do that. So the water table is 2.5 meters below the base of this. So if we know the advective velocity for the plume to go down there, the solubility, so the maximum concentration can be the solubility. And if the gas, volumetric gas content is 10%, and I think in this particular case the total porosity is 35%. Seems to be a number that we've used already today. I don't see it right now, but I think that's right. Then we can calculate from the infiltration rate. Infiltration rate is 45 centimeters, half a meter of rainfall a year. Not unusual for this northeastern North America. The volumetric moisture content is 10%, and so it travels at 4.5 meters a year. If it has to travel 2.5 meters, so the time, I guess, is just going to be equal to 2.5 divided by 4.5 meters a year, which is about 6 months, which is where the previous number came from. We know that it may be retarded. And so this assumes that this is conservative in this particular case. If it was retarded and we had a retardation coefficient added to it, then I suppose the time taken would be equal to this multiplied by the retardation. So if it's equal to 1, it's just this. If it's equal to 2, it'll take twice as long to get there, etc. And so, yeah. So T is just equal to length times retardation divided by advective velocity. That's the only expression we've used. And so the other thing we might be interested to calculate is the mass loading by being carried in the aqueous phase. And so again, we can do that. It's just the product of the advective velocity multiplied by the volumetric moisture content. Volumetric moisture content. Advective velocity was 4.5 meters per year. The volumetric moisture content is 0.1. This number together is actually equal to Q infiltration, which is also equal to 0.45 meters a year. By definition, this term is equal to the Darcy velocity. Darcy velocity. Both of those. And the solubility, the maximum concentration of TCE in water is its solubility, which is something like 1100 milligrams per liter. So if you multiply these by each other, this is the mass loading per meter squared, or per unit area squared. So it's in meters cubed per meter squared. So this is, the units of this have to be a velocity multiplied by a mass per unit volume. And so we end up having an imbalance in terms. So we have to actually, to get the areal component, we have to multiply by an area. And so that gives us a mass loading, if we multiply this, of 450 liters per meter squared per year. And if we multiply this out, we multiply 450 liters times 1100 milligrams per liter, we get a half times 10 to the 6 milligrams, and this is equal to, per meter squared, 10 to the 6 milligrams is 10 to the 3 grams, which is 1 kilogram. So 0.5 times 10 to the 6 gives you half a kilogram per year per meter squared, which is dissolved in. So you just have to be a bit careful with the units and realize that this is a mass loading per meter squared. And so if you have 10 meters squared that are covered, you have to multiply that by a factor of 10 to be able to get 5 kilograms for the total plume. So you can use more sophisticated ways to do this. You can use numerical models to do this, and that's exactly what's done in this particular case, merely to prove a point, and that is that if you then go back to this condition here, the third of our cartoons, if I can get to it, which we really didn't deal with. And so the third of our cartoons includes diffusion that can operate, the effect of rainwater washing this down into the groundwater zone, but also the effect of the fact that these vapors will be denser than air, and by negative buoyancy will tend to sink, and will also contact the water, the groundwater zone, and can be dissolved in the system. So if we now look at all three of these behaviors, not by defining the response, but by just looking at a model that defines that behavior, then you can see what the various effects are. And the two effects are just shown in these little cartoons of doing two things. So the cartoon represents the fact that this little box of TCE is placed here, and around it there's this slice of cake that defines the behavior. So if you imagine taking the box that looks like this and looking at the symmetry, so the symmetry would be a section that would go through here and would go out here and go out here like this, but would kind of look like a slice of pie. If you look at this. And so if you look at the migration of the vaporized contaminants as it goes through here, both by diffusion like this, by the sinking of the vapors, which are denser than the air that's in the pore space itself, but also add to that effect the influence of rainwater washing down through this and carrying this portion down to this. And you can look at two things. You can look at the distribution of these contours, of how far the volatilized plume has traveled horizontally in the system. And you can also look at the effects of its contact with the groundwater zone that exists underneath all of these. And so these on the left and right represent two different behaviors. The left represents the case where it's the source is placed here, but the site is just left to do its own thing. And the right-hand side represents the case where the source is put in here, but there's a membrane that's placed on the top that stops infiltration of water into here. So here, infiltration can occur, and we'll wash the stuff down. Whoops. And here, that can't occur. And they look at times of 6 months and 1 year in the 2 second ones. And so you see that actually these contours are relative concentration. So relative concentration of 1 in the box, a tenth, a hundredth, a thousandth, a 10,000th. In both cases, if you compare left and right, they've gone roughly the same distance, maybe slightly shorter in this case, which is interesting than in this case, if I'm looking at the right ones. No, actually this is, oh no, this is 3 zeros, and this is also, yeah, so these are the 2 same ones. So this one has traveled slightly further by the looks of it in going out. But and if you look at a year later, then they've traveled a bit further, not twice as far, but slightly further, because it's a diffusion expression, and it's driven by the concentration gradient. And of course the concentration gradient would be between these 2 concentrations over this particular length, right? So if you wanted to calculate the concentration gradient, you could do that, I suppose. And it would be this magnitude here. So this would be 100th, this is 1,000th, so this would be almost 0.01. I guess it would be 0.099, right? 990. And this length would be, if I look at these lengths, this is 4 meters, something like this. So if you wanted to, you could calculate the gradient to use the diffusion equations. But because it's already reached an equilibrium, it's not changing very much between this part. But what's quite apparent is if you look at the loading that's occurred in each of these, is that in the isolated case, 6 kilograms have gone into the groundwater system, and here less than a tenth of that has gone into the groundwater system. And so you have to conclude, I think, that since the contour of concentrations along this top surface is pretty much the same in both the left and right side, then it's not being driven by this contact of the vapors with the top surface, but it's merely being completely controlled by the amount of fluid which is being washed down by infiltration and getting here. So in other words, it would arrive here in the groundwater zone, and then it would be transported away from there from this. And so clearly the influence of advection carried by water is much greater than the influence of diffusion carried on in its single form. And so that allows us to be able to at least make some evaluations for those behaviors. So I suppose the other thing that you could do is you could apply the same kind of analyses using these expressions here to be able to look at what happens if you circulate gas or air through the system for soil vapor extraction. You know the equilibrium concentrations that you can pick up from the maximum solubilities, right? So you could calculate, for instance, if you know Henry's Law coefficient is equal to the concentration in the gas divided by the concentration in the liquid. For TCE, we know, for instance, that concentration in water is something like 1,100 milligrams per liter. And so if we know the value of the Henry's Law coefficient, which I think is of the order of 1, then we can calculate the concentration in the gas form, if we know this. So we know this roughly, we can calculate the concentration in gas, and so we know that loading. And then if we want to calculate the mass rate of removal, it's just going to be equal to the volumetric flow of air multiplied by the concentration in gas. If we know the Rowels Law coefficient, and we know for any particular component the aqueous solubility, the maximum concentration, we can then get this value. Once you know this, and if you prescribe a volumetric flow rate, then instead of, you could just look at pumping that volumetric flow rate across here and get a rough idea of how quickly you could remove the mass. If you calculate how much mass is here, then just as we've done before, the time taken to remediate is just going to be equal to the mass divided by the mass rate of removal. Kilograms per time, one divided by the other just gives you time. And so you can use the same kinds of calculations that we've attempted to use before, but apply them in this particular case to, instead of water being the component that carries TCE dissolved in it, air is the component that tries to carry TCE in it. And of course we'll remove it from the source zone. And depending on how fast your airflow is and for how long you do it, depends on whether the rate it takes, the length of time it takes to remediate a site. So that is kind of it, I think, for vadose zone behavior. It all revolves around these three kind of mechanisms. They're direct analogs, I suppose, to flow in the vadose zone is that we have an advective flux, which we can define in some way. There's a diffusive flux that we can define in some way, and we can make a distinction between conservative and non-conservative behaviors, but just by defining this retardation coefficient. And so long as we're careful in understanding exactly what that is, then it allows us to be able to apply all of the concepts for advection and dispersion that we talked about for the saturated zone, also to the vadose zone. So, and therefore be able to apply that to remediation. So that's it for now. The remaining material to deal with is primarily talking about modeling. I guess if you go back, I don't know, I guess I have the syllabus in here somewhere. I'm not sure where. So the materials to talk about, remaining materials to talk about are in mathematical models, which we won't talk about until after the break. And then we'll talk about how do you get all these weird and wonderful properties that we've talked about. Permeability, fractions of organic carbon, distribution coefficients, porosities, permeabilities, capillary pressure versus saturation curves. How do we get that information when you go and stand at a site and basically you're standing in a field? And so that relies on drilling and other methods of characterization, which we'll spend about 3 weeks doing after the break. And then the remainder is the remediation presentations, and that's it. So now hopefully we understand something about the physics of free phase flow in porous media, the mechanisms by which stuff gets dissolved and gets carried by diffusion and advection, what the controls are, what happens when that is either conservative or non-conservative in the groundwater zone, and how that also applies above that in the vadose zone. So we've got all the kind of mechanical tools in terms of the physical understanding of what's going on to be able to make a stab at remediation methods which rely on those processes of not stuff getting into the system in the first place, we now know that, but using the same principles to be able to remove it. Pumping water through it to dissolve it, pumping gas through it to volatilize it, and other various mechanisms that can change the physical properties of the subsurface to allow that to happen. Okay? So I'll leave that for now.